Hey guys, welcome back. We got chemical kinetics today, all right? And so when we talk about kinetics, we are talking about the rates and mechanisms of chemical reactions. We know we have reactants, right? So you guys know reactants react. And they're going to go to, oh, the arrow didn't draw. We're going to go to products. So reactants to products, okay? And we've talked a lot about, at this point in chemistry, the reactants, the state of the reactants, how many reactants, whether it's a mass, whether it's a concentration, whatnot. And then the products, and then if energy's in or out or whatnot. We are now talking about the arrow, right? So we're going to talk about the arrow today, right? And that was what we're going to talk about. So in order to react, let's say we just do a reaction. Let's give it a real one. Reactants. C3, well, let's make it even easier. Let's make it H2 gas and O2 gas. And that's going to yield H2O. And of course, it's a 2, 1, 2 to balance it. All right, in order to react, all right, I have my H2. Try to make them the same size for you. There we go. So you got H2, and we're going to have O2. And in order for this to react, right, H2 and O2 to react, what do they have to do? They're going to have to collide with one another, if that makes sense, right? We're going to have to collide. Somehow we're going to collide. Now, when this is a little foreshadowing, no matter how oxygen and hydrogen hit, right, you're going to get O and H meeting, right? So the orientation of this collision is not very important, but they must collide, right, to react. So this molecule and this molecule, right, the particles or molecules must collide to react. Right, they got to react, okay? Now, this leads us to collision theory. In collision theory, right, what we're going to get out of it is that the reaction rate, right, is directly proportional to the number of molecular collisions per second. All right. And so when we talk about a rate, we're talking about how fast, right? How fast something is moving, how fast something is going. In this case, how fast something is reacting, right? Now, there's something called an effective collision. All right? And this is one that results in a reaction. All right? So when that hydrogen and oxygen meet, there actually has to be enough energy in that collision for it to react, right? Just like if we use propane. Some of you guys have a propane grill. And if you just turn the gas on, let the gas out into the atmosphere, nothing happens unless it's lighted, right? So, right, we're going to talk about that real quick right now. And if we look at a graph, all right, we have a y-axis here, and that would be our energy, our relative chemical potential energy. And we got well, I didn't want to do that. I want to do this. We have an x-axis, and just think of this as the reaction pathway. And kind of how it's done. Our reactants will have some type of chemical potential energy. So in our case, this is our reactants. I got H2 and O2 up here. Okay. Now, we have products over here. And this would be our H2O. Two of them and two of those. Now, this you might recognize, right? The difference in energy between the products and reactants is delta H, right? We talked about that before, enthalpy change, right? The heat transfer at constant pressure. So we could use hydrogen as a potential heat source or fuel source because when hydrogen and oxygen react, produces heat, right? And that's the delta H, okay? Now, the path to go from reactants to products, right? As you know, whether it's hydrogen, propane, or any other fuel, it just doesn't happen. We need something to ignite it, right? A lot of times. Now, some things happen without igniting them, but a lot of times we need to ignite this. And so there's the reaction pathway, right? Is that this is going to kind of go uphill a little bit and then come downhill, all right? And this hill, the height of this hill, how tall this hill is, right, from our energy here, is called the activation energy. Okay, this is big. And this is the minimum amount of energy required for the reaction to occur. All right. And so if you think about this, you'd have H bonded to H up here. You have O bonded to O up here. And up here, this is what we call the activated complex. All right. Which is a transition state. All right. So what that means is that if we get the minimum energy, all right, think of it as if you're a ball on a hill. The ball could still roll back down or it could go forward. All right. And so at this point, when we get the activation energy is met and we're at top of the activated complex, we can either go forward to the reactants or go forward to products or come back to the reactants. All right. Now, with this, the orientation of the activated complex is important. Okay? Which is the orientation of the collision. So that's kind of important. All right. Now, in hydrogen and oxygen, it's not important at all. No matter what, H and O are touching when hydrogen and oxygen meet. Okay. In propane, it's not as important. But when we get to bigger molecules, especially if you think biological molecules, orientation now becomes hugely important. All right. Okay, so some reactions, the orientation is, especially with bigger molecules, it's very important. Smaller molecules, atoms, orientation is not important because no matter what, the orientation is kind of correct. All right. So when we talk about rates, all right, when we talk about this reaction, we know that our reactants, after this activation energy is met, we're going to actually revisit that later on. Okay, but when we talk about reactants and products, we're talking about the speed. Once EA is met, we're going to talk about the rate. So the reactants, and we know when we have hydrogen, oxygen, or propane or whatever, the concentration will decrease. And the products, whatever our products are, we know the concentration increases. Or amount increases. Okay, so concentration decreases in products with time. Right? It's a rate. So when we think about a rate, right? Think about, physics class, if you ever took this, delta X over delta T, right? What would that mean? That means the change in position and direction X over the change in time, right? And so, for example, take an easy example. If you go from 0 to 60 miles in 0 to 1 hour, right? So if you go 60 miles in 1 hour, your speed is 60 miles per hour. That makes sense, right? And so now you don't necessarily have to drive 60 miles to be going 60 miles an hour, right? You can accelerate to get to that rate where you would travel 60 miles in an hour if you drove that long. All right? Now, that's speed, right? We're going to talk about concentration. All right? So for chemistry, our rate would be the change. Now we're going to have this bracket here of, I'm going to use R, reactant R, right, over the change in time. Right? Okay, now, a lot of times it's going to be negative. Why would it be negative? Well, the rate is going to slow down with time. Now, a lot of books will use it this way where the rate is negative change in concentration at A with change in time. And these brackets, right, this means the molar concentration of A. So the molarity. So those brackets mean molarity. Okay? So if we look at the rates, if we do a graph here, the rates, we of course would have time here. And I'd have our concentration, let's just say concentration of H2. Right? In this case, or R, or reactant, right? Well, what's going to happen? It's going to start at time 0 at whatever our initial concentration is. Right? Let's just number of molecules, right? And it is going to decrease with time. Oh, I didn't want it to do that. Okay? It'll decrease with time. Our product here, concentration H2O, or whatever product we have, will increase with time. All right? If that makes sense. Hopefully that makes sense, right? And so there are the rate here. We don't usually often express it in the rate of water formation, right? We can, but we normally express it in the rate of hydrogen decreasing or oxygen decreasing, right? They'll have their rates, okay? So as the reaction proceeds, right, the concentration of H2 decreases, right, and the concentration of water increase. Now, what else was here? We had O2, right, as well. And so O2 is going to have a different graph. All right, so O2, right, if we started, let's say here, O2 will have something different. All right, concentration of O2, right, which is a reactant, also decreases with time. However, it's not the same rate. Now, my graph is not perfect, okay? Right? So O2 is used, well, how do you think it compares? That's a great question. O2 is used at half the rate of H2. Why? What's 2 H2 plus 1 O2 to make 2 H2O? So I need twice as many hydrogens as I do oxygen. So hydrogen is going to be used twice as much, it's twice as fast as oxygen. All right? And so the relationship is determined by stoichiometry. And so now this leads us to the relative rate. All right? So the relative rate. And that would be the rate would equal negative change in concentration of H2, change in time. All right? It's negative because your concentration of H2 decreases. As the reaction proceeds. Right? Also, the reaction rate slows as the reaction proceeds. All right, so it's going to slow down. All right, so if we look at these relative rates, the rate of, now this is for the reaction, the whole thing. This is the reaction. Would be equal to, well, I don't want to go back. Equal to negative change in concentration of H2. Oh, what? Sorry, I messed up. Let's try this again. So relative rates, H2 has a coefficient, right? It's 1/2 the change in concentration of H2 with the change in time. equals negative. Now oxygen has a coefficient of 1, right? In fact, let me make it sure. Let's make sure we get where the coefficient is. The coefficient's on the bottom. Change in concentration of O2. Change in time equals positive 1/2. Change in concentration of water. Change in time. So that's the relative rates of the reaction. How hydrogen, oxygen, and water would be to each other. Okay? All right. Now, when we do a relative rate, all right, these are numbers. So I want to point this out. That is a number, and that comes from the coefficient in the equation. Right? That's where that came from. This 1 came from that 1. This 2 came from that 2. All right? This is just a number. That's just a number, okay? Like 15 miles an hour is just a number, right? It's a rate. 15 miles an hour is a rate. So if you had 5 molarity per second, that's 5 moles per liter per second. That's a rate. So if, whatever rate you're using, hydrogen, that's the rate, 1 molar per second, 2 molar per second, right? And this is also a number, and these are just numbers, okay? And the rate is just a number, so they're numbers, right? That's what we're looking at. So if we look at the rates, we're going to talk about rates because sometimes there's more than one rate, and I want you to know what rate we're talking about. So again, if we have time here, and we have the concentration of whatever reactant, we'll use H2 again, just because we have been. All right. Start there. Something like that. Okay. Now, there is something called an average rate. Okay. And this is just the rate over a period of time. It could be the whole thing, right? Okay, it could be from 0, right, times 0 down here, all the way to whatever time t down here. You could have an average rate overall, just like your car might have an average speed. Right? You might have that setting. Newer cars will tell you that. Oh, you're averaging this. Okay? It takes into account all the time it's on. Right? And so if we took of an average rate, right, these two here, right, this would be the change in concentration of H2, change in time, right? That would be your average rate for this time, T1 and T2, right? That's an average rate. If we compare this to driving, your average rate is your average rate. So if you drove 15 minutes to whatever place, right? And you found the distance and it was 4 miles, you can do the average rate, right? So 4 miles, and you change that to an hour, right? It's a quarter of an hour, right? You can do your average rate, right? Which is not very fast, right? 4 miles in 15 minutes, that's not breathtakingly fast. However, the police officers don't care about your average rate, do they? They care about your instantaneous rate. Okay, right, and that is the rate at one point. Right, think speedometer. Right, and this is right. Most of what we mean with rate. All right, and so my rate right there, okay, my instantaneous rate would be the tangent line. It'd be the tangent line, if I could draw a tangent line. It'd be a tangent line right there. That makes sense? Which, those of you who take calculus, the derivative. Okay? All right? And so that would be your instantaneous rate. And the police officers care about your instantaneous rate because you might have a very slow rate, average, but then you got frustrated, put the gas down, and you were going 45 and a 25, and they don't care that your average rate was like 10. They care that you were going 45 and a 25 at that instant. Right? Same thing here. So we have an instantaneous rate and an average rate. Now, there's also, right, an initial rate. And this initial rate is the instantaneous rate. At time 0, right? So it's right there. That's your initial rate. Okay? And that's usually your fastest rate. Okay? So those are the relative rates. So let's dive into an example. Skip down to relative rates. All right? So when we talk about relative rates, right, it says the oxidation of ammonia to form nitrogen dioxide, water is formed at a rate of 42 moles per liter per second. And you got 3 questions. All right, so my recommendation for these types of problems, always, this is always my recommendation, is to write out the balanced chemical formula, right? Our balanced chemical equation. So ammonia, NH3. I'm not worried about state symbols. That's a gas, right? But not worried about that right now. All right, oxidation, O2, to form nitrogen dioxide, NO2, and then water is also formed. All right. That's probably the hardest part right there, guys. Just throwing that out there. For Chem 2, that's usually the hardest part. Okay. Now we got to balance it. All right. If I look, I got 3 hydrogens and 2 hydrogens. Right? 3 and 2. So that means I'm probably going to have to double this. Right? Which means I have to double this. And then I have to put a 3 here. But now that's 6 and 6, good. But oxygen now has 3. So now I have an odd oxygen. So let's see what this can be here. So 2 nitrogens is good, right? 6, good. So I have 2 here and 3, I have 5. So I'm going to put, right, no, I don't have 5. I have 2 times, I don't have 5. Let's do that. That's 4. And 3 is 7. 7's better. So that's 7 halves. So this becomes a 4, a 4, and a 6. Let's double check. 4, 4, yep. 12, 12, good. 14, 8, and 6, 14. Excellent. All right. So I would write down now the rate of our reaction. All right, it's, well, let's do that. Make sure we get the negative 1 over 4, 1/4, the change in concentration of ammonia, change in time, equals negative 1/7, change in concentration of O2, change in time, equals positive 1 over 4, the change in concentration of nitrogen dioxide, change in time, equals positive 1/6. The change concentration of water, change in time. All right, so that's our relative rates. I wrote those out. Now, which one we know? We know water is this. So water is 42 molarity per second, right? So that's what this number is at that time, okay? And I would write this out until this becomes very, very concrete, because this is new. All right, again, remember, this is just a number, like, all right, this is just a number, this is just a number, and that's a number. All right, they change, but they're just numbers. And so we know that if we come down, rate equals 1/6 the change in concentration of H2O, change in time, which is the same thing as the rate equals 1/6 times 42 molarity per second. So that means the rate would equal what? Well, 42 divided by 6 would be 7. So the rate of this reaction is 7. Now, how can the rate be way different than the individual components? Well, it's no different than like in a car. If you're taking a car and you're taking a turn, and you take the turn at whatever speed, let's just say 10 miles an hour, the inside tires, whatever way you're turning, the inside tires are traveling slower than the outside tires. And the inside person is traveling slower than the outside person, right? So you're all in the same car, and the overall car has a speed, but tires are going different, right? So they have to be independent, right? They rotate differently. The people inside are technically going different velocities on a turn, which is kind of crazy, right? We don't think about it that way, but we are. And so the reaction has an overall reaction speed, but because we have coefficients, each individual component has a different rate relative to the overall reaction. So now we know the rate is 7. All right. So now O2 is right here. So we're going to come down, and the rate is equal to -1/7 change in concentration O2, change in time. Excuse me. So that means 7 molarity per second is equal to 1/7 times, I'm just going to put in a big old X. All right, because that's what we're looking for. Well, what does that happen to be? X equals -49, right, molarity per second, which is the change in concentration of O2 with the change in time. That's the rate, -49. So this is -49 molarity per second. NO2 formed, all right, same thing. Rate equals 1/4 the change in concentration of NO2 with the change in time. So that means 7 molarity per second equals 1/4 of whatever NO2 is going to be. I'll use green. So that means X would be 28 molarity per second, which is the change concentration of NO2, change in time. So that's 28. And the rate of ammonia. So ammonia is -1/4 change in NO2, change in time. And so 7 molarity per second equals -1/4 of X. So that means X would be -28 molarity per second. Change in time. All right. So that is how we do relative rates. All right. My recommendation always is to write out this balanced chemical equation. Right. Always write out that. Then have this done, so you know how the rates compare to each individual thing. Then take whatever information you're given. You might be given, in this case, we're given water. You could be given this one. You could be given the rate of the reaction. Whatever you're given, and then you can find what the other rates are relative to what you're given. All right, hopefully that works. All right, guys, if you have any questions, don't hesitate to reach out. Otherwise, we'll see you in the next video. Take care.